I'm just
Sloan's
weird.
like, that time I get up there, it's like,
Yeah, see the big tree, it's like,
so,
you've seen one, if you come here whole life without seeing one,
when I practiced it.
you were actually like avoid most people. If you were
Okay.
facing one of those three cities.
So we'll talk about a couple things in analyzing some of the 2x2 tables today. We'll go over what a Fisher exact test was, and look briefly at the examples there to clarify what that is, since it was kind of rushed at the end of last time. And then there's another test called Mantel-Hansel test, or Cochran-Mantel-Hansel. Cochran is the advisor of my advisor, so I usually put that in there. So it is for stratified 2x2 tables, or series of 2x2 tables in different groups. And then sometimes this is done for accuracy. We also deal with confounding, that there can be different relationships in different proportions of success, even if the same odds ratio is present across different groups. So it can kind of obscure some effects that might be there unless you stratify and account for another variable. So the Fisher exact test, we have a 2x2 table where there's rows and columns, and if these are the counts that are in there, there's A plus B in this row, and A plus C in this row, and C plus D over here, and B plus D over here, and then N is the total. And we're asking, are the two, so this is variable 1, and this is variable 2. And so variable 1 might be a treatment and control, randomized treatment assignment. It might be something observational, male, female, high school graduate versus not. And variable 2 could be some type of outcome. This could be retrospective, where we've seen who has disease or not, and then looking back at things associated with that. It could be prospective, where we followed people over time and seen this. Or it could be all one time period, and these are just observational variables. But in either case, are the variables associated with one another's? Together, so that the chance of a response, in one row of the other variable is different depending if you're on row 1 or row 2. Are the response to column entries, are they different or not? This could be phrased as independence. You're thinking about these as independent. If one of these groups is like treatment control, and so these numbers are kind of fixed, it's usually phrased as, are they the same proportions, kind of homogeneity of proportions. But in any case, are things independent or not? Right. If they are, the expected count in cell 1-1, where we observed A, so in this one here, is calculated as the row. Oh, darn it. Put that up. So the expected number is the A plus B times A plus C. Clean that up. Right. Over N. And so that could be, why do we have that? Well, if you write it this way, you see that it's the proportion in the first row times the proportion in the first column times the overall sample size, and one of these you just cancel. So independence means you multiply probabilities together, and that's what we would get. So if A is bigger than this, we're going to consider all the tables where A keeps getting bigger up to a limit. Right? If A is less, we would look the other way, But let's just consider one of these, right? So if A is greater than or equal to its expected value, right, then we're going to enumerate tables away from expected values that are at least as extreme as our observed table. What do I mean by that? If we have A, B, C, and D here, right, with these fixed margins, right, we can consider a table that's going to be farther away from the expected value by making A bigger. Right, so the next table in line, we put A plus 1, but we keep the margins fixed. Right? So if this goes up, this one has to be B minus 1, this one has to be C minus 1, and because everything still adds up to N, this thing has to be D plus 1. So that's the next table that's pulling away from independence. Right? If A is bigger than expected, this is even more so. Expected counts are exactly the same for that table with those fixed margins of independence. And then we would keep doing that as long as we can. A plus 2, B minus 2, they add up to A plus B. C minus 2, this adds up to A plus C. Same margins, same expected values. This one has to be D plus 2, etc. To the point that we can't do it anymore. At some point, you hit a 0 cell in one of the, you keep making this go down, it can't go below 0. So it can only go up so much, and so on. So we have these tables enumerated, and then we're going to, under the hypergeometric distribution that has these fixed margins, calculate the probability of every table. Right? Add up all those probabilities, and twice that is our p-value. Right? So our p-value, in kind of words, right, the probability of getting a result as extreme or more extreme than we got if the null hypothesis is true. And so if this is more extreme, these things are more extreme, away from bigger than the expected value, same expected value in all cases. Right? And so the probability of a table comes from this hypergeometric. So the probability of getting the table A, B, C, D, for instance, in there with fixed margins, there's N overall, and we're choosing A plus C to be in the first column. And then how do they split into the rows? Well, in the A plus B row, you have A, and in the C plus D row, you have C there, and that's the probability. And as you adjust the A's and B's for those other tables, the probabilities change. Right? And so the p-value for testing the hypothesis is twice times the sum of the probability of a table over the list of tables that I made on the other page. And if that p-value is really small, less than 0.05, that means the probability we got something as extreme or more extreme than what we saw is rare, and we reject it. So rejecting 0, p-value is less than 0.05, and then if that happens, which means not independent. Rejecting the null hypothesis means that there is an association. In many cases, this will correspond to what we got for the chi-square tests, if you do that testing, but this doesn't depend on normality, it doesn't depend on large sample sizes. Even really bitty, tiny tables, you can calculate this. Right? If there's only a few tables, though, there might only be a few probabilities, so some tables might be hard to get ones that are much less than 0.05. Okay, so the data for last time, the directory of things. This is the R script we have for last time. So there's this one promo table from the textbook, male and female resumes, and whether they were accepted or not, promoted or not. Right? And it appears that male resumes were accepted. So one study of bias that could be there. There's the table margins are 24, 24. So they're equal, 24, 24. So if it's independent, we'd expect it to equally split across males and females. The yes and no's, but there's obviously a difference. The chi-square test gives you a p-value of 0.025 or 0.05 to take that give a warning. Oh, almost not there. There you go, now it's all there. Right, it gives it that p-value of 0.02. Let me see, one was with the, that's without the continuity correction. With the continuity corrections a little bit higher. The Fisher test does this one, and it gives a p-value of 0.05. It also gives this confidence interval for the odds ratio, which is kind of interesting. So what could be the probabilities of the different, which values of the probability of P1 are rejected or not? Right? So if they're not rejected, then they're in the confidence interval, and it changes it into an odds ratio. It changes it into, right, the Fisher test. The odds ratio is the probability of being in the first cell, right, over the probability of being in this other cell divided by the probability that you're in, say, the 1, 2, cell 2, 1 over the probability that you're in cell 2, 2. This gets estimated. It gets estimated as a ratio of A times D up here and B times C down here. And the probabilities of that you're in the first row, the first column in the first row, divided by that you're in the second one, and then divided by the ratio of those probabilities. In the second one, it's an odds ratio. But so that also comes out of that. If that's 1, then the ratio of these probabilities is equal, and they have the same odds. Right? So the probabilities are equal. Right, and so it comes out to 0.0489. Not a big sample size. It appears to be at the edge of statistical significance. It certainly would be enough to alert people that, hey, maybe there's something here, maybe we need to confirm this in other ways, and it seems to be some real effective difference. There is a hypergeometric function in R. So, it takes a little bit of reading to figure out what all these different symbols are. The hypergeometric is often phrased in terms of, urn with black balls and white balls, and you pick out a certain number, and you see how many out of those, out of your sample, out of your population are black and so on, and white there. And some probabilists go with that and do all different types of schemes with 2 or 3 or more colors and different sizes and so on. But anyway, you can calculate probabilities. So the probability, P hyper, is the probability you're at a number or less. So we had 21. So the probability you're at 20 or less, 1 minus that is going to be the probability you're 21 or above. Right? Our expected value is 17, and we have 21, so we're looking at all the tables that go bigger. And so the probability you're bigger is this. There's 24 males, 24 females, 35 overall, and we got 21 actually in the group of males, but 20 or less, and then 21 or above is the split, so it's done this way. And so that's that probability. The p-value is twice that, right? And that's what the Fisher test gives. If you added up the density, the probabilities at 21, 22, 23, up to 35 in that first cell, some of them might not be possible, might have zeros. You can't actually have 35 up there, 24. So it must stop at 24, right? 21 to 24. This number, just to confirm that, I think, what if we stop at 24? Does that give us the same number? Or, yeah, essentially the same number. You only can go up to 24. Right there. Anyway, here's a different example. Do you have any question about it?
No,
just stretching. So, this is a book on fundamentals of biostatistics by Bernard Rosner. And it's a retrospective study of 35 people who died from cardiovascular disease and 25 who died from other causes, and then asking did they have high salt diets. Right? Where did warnings about sodium and blood pressure and things come from? Well, probably observational studies. We had people dying of CVD and then others, and then somebody looked back and said, well, why are these people dying of this? And others are having strokes or cancer or something different. Is there an association? And so there were 25 non-CVD and 35 CVD deaths, and this is how many had high salt diets or low salt diets. Again, kind of a small sample size there, and to try to test independence in this, here are the small expected values. The chi-square gives this warning that the chi-square approximation might not be correct. So meaning the p-values might not be all that useful because it's not all that normal. Right? The p-value with this one, with the, let's see, I run that thing, right? So it's almost 2. The uncorrected one without the cut gives a p-value 0.4546, so no real association. As you get do the correction, it's a pretty big change in the p-values and in the statistic values, kind of relatively. It's kind of warning you that it might be small. The Fisher one, though, doesn't give any warning. It estimates the odds ratio. And it also comes up with this p-value that would be not significant at all. There's a chi-square test where you can simulate data. That ends up being equivalent to this Fisher test because it's simulating under the fixed margins and seeing how many tables are extreme like that. So there's a way to simulate it. That's very close to the Fisher's test, the simulation. And you can simulate tables, this random hypergeometric samples. You can do that, simulate a number, and we've got only 2 in the first group. So here's the matrix. There it is. Only 2 up there. If we sampled with something where we had 7, right, and 53 and 25 and 35, what's the chance we would only get 2 up there? That's this probably 2 or less. Right? That's the extremes. You can simulate that under the hypergeometric. So let's say you simulate 100,000 times, 25 or 35 with 7 events. What's the chance that you're going to get smaller than 7? If that 7 is going to split and you're only going to get that. Well, that happens about 37,000 times, and then twice that would be a p-value, very similar to kind of the simulated p-value from this Fisher question. It's a little bit higher, but anyway. So it deals with this independence through the fixed margins without making this chi-square normal type assumption. Right? So if you have data that are small at all, and you're trying to report and make a claim that something is statistically significant, you can reinforce the conclusion by doing it in multiple ways. If it ends up being kind of on the border and not significant, you have something to think about. If it was kind of a preliminary, smaller study, it can suggest more studies. If this was your big study to prove something, and you've really staked a lot on it and it doesn't quite come out, you might have an issue with trying to proceed with further research on that topic, or getting people to give you funding to do more research in that area. But if multiple ones of these are also not significant, then it doesn't seem to be there. Okay. But any questions about those? So the extension of these things, is where is this Cochran-Mantel Hansel test. Right. And so the scenario here is we have multiple 2x2 tables. And we might have treatment and control here, and then we have a positive outcome and a negative outcome as one 2x2 table. And so here's A1, B1, C1, D1 here. But this would be the data just from, say, center 1. Right? A lot of medical studies are done on multi-center sites so that they have a better chance of recruiting patients. D1, not D2. Okay. And then at the next center, you get another table, a treatment and control, A2, B2, C2, D2 here, N2 is a sample size here. Here's center 2. On to the next center. I don't remember what, it's called K. So AK, BK, CK, DK are the counts for positive and negative, treatment and control. And N sub K is the same. It's some there. So the total sample size is N1 plus N2 plus N sub K. And one possibility is just to merge all the data together and analyze, add up all the A's, all the B's, all the C's and D's and just get one table. But that can obscure some things. Right? You could have the center is essentially, a stratification variable. It could be kind of an underlying variable. If it's not observed and not paid attention to, it could be called confounding. That there could be a real difference here, but if you have a bunch of patients in one center where results are quite poor, that might overpower, kind of swamp out the effects, the differences at other centers. So if there's a small center with almost no effect and a big center with a really big effect, it also can make it look very big, but it might not apply to every place, right? So it might be a confounding. So we want to test whether there's an association between treatment and control and positive and negative, but accounting for this other thing, right? And so the procedure, right, for doing the test, right? So the hypothesis is positive, negative is at the same rate in treatment and control. Kind of the split between positive and negative is at the same rate, so it doesn't depend on whether you have treatment or control. And the alternative is there is an association. Right. So the procedure for testing this is we're going to calculate the expected value under independence in each cell. So E sub I in center I is going to be the AI plus BI times AI plus CI over NI in center I. That expected value has a variance. The variance gets estimated as it's a longer formula. AI, so this proportion times this one. And then AI plus CI over NI, and then BI plus DI over NI. And that is an NI over NI minus 1. They're kind of a little adjustment term. Now this looks big, right? But it's not as complicated. So if you write this other way, right? So that it's NI times a proportion and another proportion. Well, this is, if this is a proportion and this is then 1 minus that proportion. If this is a different proportion, it's like a QI, 1 minus QI. And so it's kind of like a P times 1 minus P, another Q times 1 minus Q, another proportion. So both of them look like binomials, right, in there. And then it's times n. Each of these would be kind of divided by an n. This would be divided by an n. But we're multiplying by n, so these things kind of, there's n and n. So we still end up with a couple n's down there for that. Right. And then there's a little adjustment because how the combinatorics work out and everything like that. So that's the variances. And so what we're going to do is we base the test. We're going to add up all the observed counts all against all of our centers. And I called those A's. Right, these are the observed counts in that 1 cell. We only can concentrate on one cell because once you know that one, if there's fixed margins, they add up, and so there's really one independent cell there. The expected total is going to be the sum of those EIs that we do across the different centers. The variance, if the centers are independent of each other, is the sum of the variances. And then our chi-squared Mantel-Hansel or Cochran-Hansel statistic takes the observed minus the expected. With a continuity correction, it subtracts 0.5, that squared, over the variance. And under the null hypothesis, this statistic has a chi-square distribution with 1 degree of freedom. And so we're going to reject the null hypothesis of independence if this statistic value is large enough. H0 if this statistic is greater than the 0.95 value. This is the chi-square 1, the 95th percentile. So if it gets greater than that value, we're going to reject the null hypothesis and conclude that the variables are related. So the power of this is to deal with this confounding and the fact that data can be gathered in different places where rates of disease and so on can be quite different. Yeah.
Just to clarify, that 3.84, that's the cutoff for the chi-square distribution?
Yeah, that's what this value is to be equal to. It's 1.96 squared from a normal, because the chi-square 1 is like a normal squared. If you take the square root of this, like observed minus expected over the square root of the variance, it's like a standard normal. As long as this v, this expected counts are bigger than 5 or 10 or something like that, so not too small. Right? So let's look at it in a data example. This is the handout for today. I think everybody has this handout for days. Why, did I give you a handout back there? So this is the one for today. this is the second case study in chapter 19. And so the context of this one is there is whether or not people were given the death penalty or not. Kind of it's a gruesome topic, but looking into is there bias that we can see in the data, and was the victim white or black? Right? And so if there's an association, it would suggest that juries or judges are awarded the death penalty more often based on the victim's race, which, other things being equal, would be a source of bias in sentencing, right, and need to be dealt with. But the crimes were stratified by the type of aggravation, right? Some are, almost, manslaughter, almost accidental, not premeditated, not planned, not as gruesome, right? And then the other aggravations, without going into details, are more gory, more pre-planned and things like that. So, depending on the characteristics of the crime, are you going to get the death penalty? If it's a much worse situation and crime, death penalty seems more likely, right? But if it's almost accidental, maybe two people get an argument, in the heat of the argument, somebody hits somebody and they die, right? Well, that's still murder and so on. But seems, do you want to give death penalty for that one? Depending, people have very different opinions about that. We're not going to get into that context, but we're looking to see if there's some bias. There's some different packages that do this, but there is just a Mantel-Hansel test, right, built into the basic part of R. And if you do help of Mantel-Hansel test, Cochran Mantel-Hansel test, chi-square test of the two nominal variables, nominal meaning categorical variables, right, are conditionally independent in each stratum, assuming there is no three-way interaction. There's no separate association between these probabilities across tables. And so you put X and Y in here. Well, X can be a three-dimensional contingency table in array form where each dimension is at least 2 and the last dimension corresponds to the strata or levels. So in addition to matrices, right, so you can have one number, you can have a vector of numbers, you can have a square rectangular matrix, but you can have another dimension, or you can have arrays of many dimensions. And so this case, let's see, figure that out, case 1902, right, is like this. It is in there as, well, just an array like this. It's a matrix, right? So it's not really set up like we want it to be. And so we're going to set this thing up as an array. We're going to bind together the death variable and the no death variable and set up in a dimension that has 2 by 2 by 6. Right. So it's going to take this victim, or the death and no death as the two counts, and victim, and make that into a little 2 by 2 by 2. Here's a little 2 by 2 table. And the next dimension is going to be aggravation. So it's a little moving it around. So now this death, when you look at it, is like this. So here's the little 2 by 2 tables. And then the third dimension, aggravation 1, aggravation 2, aggravation 3, and so on. Death penalty is across the top, no death penalty, and then victim's race must be there. It didn't quite capture, I think with a little bit of manipulation, you could get it to capture the characteristics, or put them on there, to make it easier to look at. The test, when you run it, it does that with this continuity correction. It gets an x squared value of 9.698. That is bigger than our 3.84, right? So it's a p-value that's small. the probability under a chi-square, you put it 9.6988, and then lower tail equals false, which would mean it will look at the upper tail, right? 50 degrees of freedom are missing, 1 degree of freedom, 0.0018, and so that's the p-value that it gets there. So if there's really no difference in getting the death penalty by the race of the victim, right? If the odds ratio is 1, the chance that we get a series of tables like we had, is quite nearly impossible, which suggests that there is some bias. And so the confidence interval for the odds ratio is larger. You always have to interpret those things in the context of the problem, so it would be best probably to look at what those rows are. But the odds ratio, if you calculate the proportions, it's a higher percentage of death for white victims versus black victims. Right? And so the death penalty, adjusted for the different aggravation levels. So if white, black, and black victims were killed, and some had, one racial victim group had less aggravated crimes, and the other one has more aggravated crimes, and there was kind of an imbalance, that could be a compounding effect. If you don't use the correction, I've made a note there that this is what the book reports for a confidence interval for the odds ratio and so on. It makes a little bit of difference. The odds ratio is the same. The confidence interval doesn't move very much there. The p-value changes, so it gets smaller without the continuity correction, but they're both very small. So it's very clear from the data that there's a difference there. Right. Now, what if we ignore the strata, the different aggravation levels? You can summarize this over 2 dimensions, save the first 2 dimensions. So it's adding over the 3rd dimension. So this array, this apply thing does interesting things. So our DAT 2 by 2 is this table, right? So there's, death penalty, no death penalty, and then the race of the victim. And if I had the labels on there, you could see what they were. But what happens if we collapse things and just do a Fisher test? Well, it's still highly significant that there's a bias. But what's happened to our odds ratio estimate and the confidence interval? If we don't stratify and collapse over those aggravation levels, we get an odds ratio of 8 with this interval 4 to 17. Highly statistically significant, so there's bias, no change there. But the estimate of the odds ratio is that. Previously, the odds ratio was estimated at 5, the confidence interval that went from about 2 up to about 16. So the odds ratio is estimated quite differently if you account for the stratification. So the degree that aggravation level is very important in these cases, and the death penalty rate is going to be much higher with worse aggravation. It seems important to account for that. Very different estimates. So under this help file, there's another example that we can look at. But any questions about the procedures? Okay. We're doing this. So these people have their names associated with this, right? Because they did the probability theory to figure out, okay, here's the variances, here's how you estimate things, you put it together, here's how you can do a test, and then probably illustrated it or did a simulation to see how it performs. Probably came up with some of the advice that, the V, you need at least 5 expected cases across these for this to be kind of reasonable. Right. We don't need to figure that out really. You can go and look at another example. So under this help file, down here is references. Alan Agresti was a professor at the University of Florida that wrote a series of books on categorical data analysis. There's kind of his big green, I don't know if these big green one, that green cover, is the most theoretical, but then he has another one's an introduction to categorical data analysis, introduction to ordered data, right? Some, this 1 through 6 is kind of an order of aggravation. So you might fit models that do more, like saying, how is the proportion increasing and so on. But anyway, so he has a series of books that are very reasonable for introducing applied data analysis and theory in this. And he has this data set here on the investigation of the effectiveness of immediately injected or 1.5 hour delayed injected penicillin in protecting rabbits against the lethal injection of Streptococci. So, the valuable research, but not nice to some rabbits. But in any case, this is how the data are set up. And so, is it delay versus response? Is what we want to know. Is there an association between immediate injection versus 1.5 hour delay versus the outcome? In many medical things, you get a modern one for people. You get Lyme's disease and you get antibiotics right away. Does that prevent symptoms? And if we wipe it out, if people wait 3 days and then get antibiotics, is it nearly as effective? So there is some modern parallels, even if like that. And the stratification variable is penicillin dose. Does this effect depend on how much penicillin you get, right? So if you wham them with a giant dose of penicillin, does it matter at 0 versus later? Versus, you get a small dose, does the time factor make a difference? So it gives you some advice there for setting up the array. This rabbits data set then is entered in R like this, where there's delay, none for 1.5, and the response cured versus died. This is where the penicillin level is 1.8. It doesn't help too much. If it's 1.4 and they get it right away, they get better. I mean, it's 50-50, right? But if it's delayed, they're still dying. This level, they all were cured, but with the delay, it's not as well. This level, one died, so it's not perfect. But even those that were delayed got better. And at the high level, they all were cured. And it was like not equal numbers of rabbits under different things. I don't know why they did the design exactly like that. Maybe they knew that if the rabbits got a huge dose right immediately, it would cure it, so they didn't test as many there. They kind of weren't as worried. So each of these are really small tables, okay? But still you can do the Mandel-Hansel test for this, and it says that there is gives a p-value of 0.047. The x-squared value is 3.93. So a little bit bigger, but enough to say there's a significant effect of early versus late treatment. There's better cure from what we saw with the data, getting an immediate dose with that, and it's significant. And small sample sizes, confidence interval for the odds ratio is above 1. That was the equal point, so it's above 1, but quite unstable with these small sizes of rabbits being tested. And what happens if we ignore dose and just add over the thing? If you apply this thing, we can, now the 2x2 table comes out like this, right? Does that look so imbalanced? Out of these 26, 16 cured, 10 died. Out of these 28, 13 cured, 15 died. 16 out of 26 certainly is higher than 13 out of 28. But you don't see many of those cases where you have zeros. It's just Fisher's test applied to this gives a p-value of 0.298 or 29. Not significant. By collapsing across this thing that made a huge difference in survival, the estimate of that odds ratio is kind of obscured. Right? The places where the small dose didn't make much difference to anybody, and the big dose everything was basically cured. Collapsing those, you get kind of an average effect, and it's harder to look at that there's. And so the odds ratio collapsed is 1.83, whereas separated was 7. It's an enormous difference, and the statistical significance changes. So stratifying really helps in looking at some of those effects. Right? But if you design an experiment and can get different levels, you might get better resolution of what's going on there. You also get, this extra source of information about dosage. Right? So for this, if you did everybody at 1/4 or at 1/2, that you would learn less of that, and probably not get better information about the cure rates. In observational studies, like the death penalty, aggravation is one factor they could point to. They look at race of victim, race of perpetrator. Could also be looked at if you had data over the years, right? You might look at, are things changing over time? What were they like in the 80s versus 90s versus now? The number of things you might stratify on and include in analyses, gets pretty big. Right? And there could be some debate about what should you actually use, right? What's important as a stratification variable. Some people who, it could come down to moving the odds ratio around, moving significance depending on what you condition on. If you condition on too much, you probably get too small sample sizes, and then it's hard to tell anything. So anyway, what I wanted to mention is this business with tables. Really, as you go on, touches on really kind of broader areas. What we're going to do on Friday and then after break for at least a day is logistic regression. Which is, adjusted models for predicting a 1-0 outcome based on X variables. Just like regression, but with the constraint that we want things are 0 and 1, and we want our probabilities to be between 0 and 1. So we use this loaded transformation. But there are many other areas that we won't really be able to touch on. But Cochrane, Mandel, Hansel, right, suggests 3-way tables, but really you can get beyond that. I've seen designs of experiments with 7 different factors being, so you really have kind of a 7-dimensional array, plus the outcomes of like 8. So you can do cross-classify by many different factors. And then the questions become things not only independence, right, but conditional independence, between variables. So maybe death penalty and race of victim are conditionally independent based on both aggravation level and age of victim and year or something like that. So it could be more complex hypotheses for how things are related. There's special methods for ordinal data. That try to build in a pattern for like increasing or decreasing relationships. So in linear regression, when we had factors that were essentially, numerical underlying. Sometimes we treated things as numerical and got a linear relationship, and sometimes we say, oh no, it's factor, it has to go up and down, right? And the same thing can be done with categorical data. Strongly agree, disagree, and things like that have an order to them, and maybe you can build a model that has more structure to it, and you can put orderings on the response probabilities, right, to kind of match something like that. It's a restricted model, and there's different ways of doing it there. With the multi-way tables, there's also something called log linear models. It's similar to Poisson regression, which in our book is chapter 22. That there's ways of putting associations of tables and interactions into a linear model statement. But instead of doing proportions, like we'll do with the logistic regression, you can model expected values. And so that would be another way of looking at that, right? The thing that does, as opposed to logistic regression, is the Poisson models have a certain mean variance relationship, so that gets incorporated. Is there extra variation? I guess that's the other thing you look at here. Under some of these log linear models, which I've always found is kind of an interesting set of models to fit and think about how they're parameterized and things. So there's ways of estimating those things. In many data examples, there's a little bit of extra variation. In some things, there's extra zeros. So you're looking at how much people are paying, the events that are happening, and if a certain thing doesn't apply to a part of the population, then you have these zeros by default. And then everybody else might be a Poisson. But you might not be able to separate out the data, and it's all just kind of mushed together. So you might have a Poisson model, but there's these extra zeros stuck in there. Right? So anyway, it's an enhancement to the model that might fit some data. And then there are some things with categorical data called latent class models. Which I did some work in. And so latent class models is there are groups in the population, but they're not labeled. Right? And so unlabeled subgroups. So when I used these in a context of a record linkage problem at the Census Bureau, so taking the census and then a post-enumeration survey and matching these things together, and without unique identification numbers, trying to decide which subsets of people were the same, like who was counted in both and who was missed, and kind of doing the matching to create kind of a 2x2 table for things. But you didn't know beforehand who was in one group, which was the other. But there's a pattern in the variables, right? And I applied that also to a kind of another mixture model, kind of latent modeling thing to in psychology in graduate school. That there was a professor in the psychology department who had done measurements on infants. So the infants would come into a lab and they'd get some experiences in a strange situation, like a new noise, a new strange person, a new strange object. And some children would be afraid of it and stay away from it, and others would go towards it. In other contexts, they would show more signs of fear or crying or more motor activity. And based on these different measurements of levels of motor activity, levels of crying, and so on, were there different groups of infants? Could they be separated in some way based on these categorical measurements? And it's kind of an open question whether there's subsets, like some are more active and some are less active. You put them into kind of polar categories, so there's more of a continuum of behaviors. But anyway, it's a way of kind of clustering or looking for unlabeled subgroups in there. So the categorical data that we've done covers a big swath of what's really done in practice, comparing two proportions, looking at odds ratios, doing some things with stratified tables. And we will do more with logistic regression, which kind of builds on this. But there's a whole area that's been developed for dealing with building bigger models, more complex models for things with categorical data. So if you go on into graduate school in an applied area and the data is primarily quantitative in nature, or you're gathering survey data or social media data, a lot of it's going to be categorical. Is something there or not, or a few levels. There are models out there for dealing with those things, and as data get big, there'll be needs for more, so. So on Friday, by Friday, there should be a posted assignment that we can do, in the following week after Thanksgiving on these things, and we'll talk about logistics progression. I'll see you before the next one.
Really?
Thank you.
Have class anymore.
Shucks.
Yeah.
I can now leave at like 12:30 on Monday, like right after data science, instead of what I was gonna do.
That's so nice. Just stay through after.
Have a good day, Professor.
Thanks, have a good one.
I'll be leaving.